All right. Uh, so, hello everyone. Uh, this is me, Rajnandan from IIT Gandhinagar. So, I happen to be your TA for the course. As you all know, the name of the course is Viscous Fluid Flow. Uh, so, I'll be your TA for the entire duration of this course, and we will meet basically on this timing, that is on Saturdays from 3 to 5 p.m. Which will be our usual slot for all the meetings that we'll have. And this course, as you know, I think you must have gone through at least by the first week's lecture series, is that it is being taught by Professor Amaresh Dalal from IIT Guwahati. uh, and I will be your interactive sessions TA, where the objective of this session, as you might be familiar with if you are if it is not your first NPTEL course, and if it is your first enrollment in an NPTEL course, typically these sessions are organized, to basically clarify your doubts if you have any, of course, in the in the week's in the week's lecture series that usually gets posted before this tutorial session, or before this live session gets started, so that you can just go through them, and if you have any doubts on it, you can basically revert back in this live session. So having said that, the main objective of this live session is basically one is, as I said once again, that is to clarify your doubts if you have in the lecture week session, and also in the assignments that you get every week, basically after the completion of the week's lecture series. So that these are the two objectives on so as to why this tutorial session is conducted. Also, it just not get limit it just not gets limited to these two aspects. We will also try to solve certain problems which in principle are aligned with the problems that you will get in your assignments. As I said, the problems will not be exactly similar to the problem that you get in your assignment, because in that sense we lose the principle of doing the assignments, right? Then you will just basically write the answer what we discuss in the in these sessions. So that's not the objective, or we lose the principle. But having said that, we will solve problems which are very similar to the one that are there in the assignments. In this way, you will learn the concepts in a much better way, which is of course what we always seek for when we are learning a course. And also it will help you in developing the thinking that you require to basically solve the problems that you will get. I hope you have got your first assignment. I think the due date is, I think it's in the first or second of February. But nevertheless, this is the idea behind having these tutorial sessions. So, once again, I welcome you all to this course. As I said, I am Rajnandan. So I'm basically a third year PhD scholar from the Department of Mechanical Engineering in IIT Gandhinagar. And I work on microfluidics, which is very aligned to this course. So the fundamentals of which is very aligned to this course. And through these sessions, we will appreciate, of course, through problems that the topics that we'll discuss in this course, which is viscous fluid flow, are indeed very fascinating, and you will truly appreciate being in these sessions. And also, just to just to have things in a formalized way, these sessions are recorded, and the notes which I will share basically from today onward, the notes which we will basically discuss in the sessions and which we will share will be posted in the website, in the will be posted in the website of this course, and the recordings will also be uploaded in the website. So in a way, if you happen to miss the session due to some of your emergencies, or whatever be the reason, you can always revert back and look for the notes and the recordings of the session. But having said these things, so you should always try to attend the live session, and that it doesn't mean that you will just skip the live session and just trust on the recordings that that will be posted, because that doesn't serve the purpose, right? Because the lecture series are anyway recorded. So just to keep an interaction between the learners, so the NPTEL team basically conducts these kind of sessions. And also, like, people like me also get to interact with brilliant minds like you, who takes the legacy of NPTEL forward. So I expect that you will join the session, but anyways, it will always be recorded and posted in the website. So that's the idea. And a few more bookkeeping stuffs. So so the link that you joined today uh, is the link that you will be joining for all the subsequent sessions. The link, the joining, the Google Meet link will basically remain the same throughout the entire duration of the course. And we will meet on usually we'll meet on Saturdays from 3 to 5 p.m. That is this usual timing as what you joined today. And unless and until there is some emergencies from my end, or there is some traveling that is being taking place at my end, we will meet on Saturdays and on 3 to 5 p.m. And if there is a shift in the schedule of this of this, if there is a shift from the usual timing of this of this allotted time, you will a priori be posted in the group, and you will also be intimated with emails from the NPTEL team, and also in the course website. So if there is no emails and nothing like that, we will meet on the usual timings from 3 to 5 on Saturdays, and the joining link, of course, will also be the same. So I hope you are clear on this. And finally, just I want to just clarify certain things before we begin with today's discussion. Is that please actively use the discussion forum of the group or of the website. That helps us to know that how far you are trying to how far you are trying to grasp a course, and where and in which areas you are finding the problems in learning, in learning the materials that you are that we share with you, basically. So that that gives us an idea about the problems that you are facing, and then also it gives us a good platform to I mean I mean, assist you in areas where you are finding the difficulty. So please use the discussion forum if you have any doubts of anything related to the course, of course. But yeah, and either me or any of the team members, of this course will always, revert back to your queries in the discussion forum. So that's the thing. That's the idea. I mean, please don't hesitate to post your queries and questions in the discussion forum, and we are always there to assist you in whichever way or in whichever manner is possible. Okay. uh, so that's the thing. And finally, just I don't want to keep it long, but finally, uh, so I'm a PMRFTA, and that is assigned for this course. So it's as a part of my TA requirement, I do these live sessions. So this is the third time that I'm doing this course, uh, that I'm being the TA of this course, and it is always fun when I conduct these sessions with 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 learners, and it helps me to keep my domain growing in this field. And uh, and also we get to interact with people and kind of know, like, so it's just a kind of a share of knowledge that basically happens from one way to the another. So I request you to don't keep this in a monotonous way, it being an interactive session. I expect people to ask doubt or stop me at any point of time if you are facing any difficulties, or, like, you want me to clarify things, uh, you know on whichever subject that we are discussing. Okay, don't just think that we will leave it to the end and then I'll ask question. It's nothing like that. Since this is an interactive session, let's just not just not keep it in a one way fashion, and rather I would appreciate if you just keep it in a two-way interaction, such that we don't lose the principle of this interactive session. Okay. And this session is meant to be for 2 hours, but it's not a hard and a fast rule that we will always we'll always take a 2 hour session, because I understand that 2 hours is a long session. So so having so like so it's a time slot that we are allotted, but like if you feel at any point of time that okay, this is being stretched too much, or like today we have done a bit of hard calculation, so we want to end it early, please let me know. And it's not that we will end in 15 minutes. That's not the principle. But it's also not the fact that it's always need to be 2 hours. Okay, it's a time slot again that we are allotted, but we will see, like, depending on how much we do in a session, and how much we learn is what is going to decide how long the session is going to be. Okay, so that's all from my end, and I will not force you to introduce yourself, but if you feel like you want to introduce yourself, you can always do that. You can type in the chat box, you can speak up, unmute yourself. It's completely up to you. But I'll stop here for a couple of minutes. I'll let you little bit settle down, and then we will start off. Then I'll discuss the agendas on the topics that we are going to discuss today. So when I say I'm going to stop for a couple of time, the floor is open for discussions, and you can always unmute yourself and speak it out if you wish to. Okay. In the meantime, I'll just check if the recording is just going on or not. I guess, yeah, I guess it's going on. All right.
Yeah, good evening, sir.
Yeah, yeah. Good evening. Yeah.
Sir, thank you so much for this session. Uh, Sir, actually, when I gone through this four lecture videos,
Okay.
it's really good from the professor.
Okay.
So, but what I'm facing is, first of all, I want to introduce myself. My name is Titus. I'm a PhD scholar from NIT Mizoram.
Okay. Okay.
Okay, so here what I'm facing is this
Yeah.
viscous fluid flow. That four lectures, he's presenting very well about that theory part and derivation part. Everything is going on, but in the assignment part, where I'm facing some doubts or issues, is that, sir, if we get any notes regarding that, some sample problems or something, some books or something shared, means it will be really good. So because the content is viscous fluid, that navy stochastic, these are going in the first week,
Okay.
but the assignment this time four problems little. Uh, I
Okay.
think little doubt in that.
Okay.
And
So
why it's because is that there is a no option type questions. It is everything that fill in the blanks type of questions. So if I missed the any decimal values, any wrong in that, also its answer is going to be wrong.
yeah, yeah, yes, I understand that. So that's a good. I mean, I thank you for asking this question. So the thing is, Titus, is the fact that not all the questions. If you see, I think if you see the assignment, I think not all the questions are fill in the blanks. Yes, there are questions. So the numerical questions are, it's obviously like you need to give the values of the answers. So that essentially is, you need to type the values basically. That's the thing. But like, you might feel that okay, in this week there are more questions where you need to basically, so I think there is one question on RTT, there is one question on material derivative, and so and things like that. So these are the things again we will discuss on that I mean, these things we will discuss. I mean, from scratch to the point where it is needed is what we will do in the live sessions. But
Yeah,
uh, so, and that you will see basically today, that although we'll not solve the problem exactly, but the similar things that we will be discussing, so what are there in the assignment is the things that we will be discussing in these live sessions. So that is one way of assisting you in the regard that you are asking. On notes, so basically what happens is that the only notes that get shared, and so these are kind of protocols that we just need to follow, is the fact that the whatever we write here, so whatever are the things that I'm going to write in in this session is going to be shared in the class, in the website, that you will see. Like, I mean, I think by today or by tomorrow the team will basically share all these things along with the recording of this session. So these are the two things that will be shared with you, which I believe will inevitably help you in solving the assignment. That's the first thing. And rather than that, you know, it's like so it's like that first you need to give a try. That's how, you know, assignments goes in any courses, be it in an online, you know, online NPTEL course, or be it in a course of your college. So so you will be given the answers, but that will only be given after you know, submit the assignment. So this is where only, you know, we can assist you in this point of time. I mean, I'll put forward this query to the team, and let's see, like, if they have some more, you know, suggestions on it. I will definitely, you know, let you know and let the group know in the discussion forum. Is it okay with that?
Yeah, sure, sir. Because this week assignment nearly four questions. I am thinking that it's like a fill in the blanks. That is a reason I'm
Yes, yes,
telling.
yes, yes, exactly.
Yeah.
So that's yeah, I understand that. So, but there is one thing that it is. So is it the first NPTEL course that you are doing, or like
Mm,
you did
no, 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 no.
this is the first?
Some other courses I took, but this is one
Okay.
of the subject advanced topic I took this.
Yes. Okay. Okay. So the thing is, for an assignment, you can submit an assignment before the due date n number of times. You know this fact, right?
Yes,
Means,
yes, yeah.
so if it's not that you can just submit it once. So it's like you can submit and your assignment on. I mean, you just give a first attempt and submit the assignment, and then if you feel that okay, I might have done this problem wrongly, or like I did some mistakes which I think like should be rectified, you can again, you know, correct your problem and then, you know, submit it again. I mean, of course, that correctness is what you are going to decide. uh, I mean, you will not be given the answers to that, of course, in before, you know, the submission closes. But you can also submit it like multiple times, and it's just not you are just going to have just in one attempt of submission of the assignment. So that is also one good, I mean, one positive way of you know NPTEL assignments that we generally share with the learners. So
Yeah.
that's
Sir, actually, one doubt, if you don't mind. Sir,
yeah, yeah.
there is one answer. It comes like a 7.9 seconds for me.
Okay, okay,
I'm not
okay,
sure that whether it's correct or wrong.
okay.
Whether I have to in that fill in the blanks, whether I have to round off and keep type the answer, or accurate 7.9 means 7.9 I have to put.
Yeah, so the thing is, if you are getting, let's say you are getting an answer of, let's say you are getting an answer of 7.9. Okay, let's say, so is it just 7.9, or let's say it is 7.191 or 92 or something like that, or it is just 7.9 that you are getting? Because I think 7.
7.9, 7.91 like that something.
Yeah, exactly. So let's say you are getting, because because this is a recurring decimal, it seems like it's a recurring decimal. So for instance, let's say you are getting an answer of 7.91. Okay, you are solving and you have a calculator, the basic calculator that you have, and you get an answer of 7.91. So now the thing is, if you write, so it's not that, so whenever you will be given, you know, you will be given the answers, you will see that it is not that you, if you write 7.9, let's say, or let's say 7.93, your answer will be wrong. No, it's not like that. You will be given a band, and that band is sufficiently, large, such that any answers in this band will be accepted as a correct answer. So for instance, the
Okay.
band so the for instance, the band will be like that. If your answer is, let's say, 7.8 to, let's say, let's say 7 point, what to say, let's say 8. If your answer is like that, so that band is some that so that band is already decided by the one who sets the question. It's not me who sets the question, in this regard. But like, it's not the fact that exactly 7.1 will only do, and if you write, let's say, 7.9, 7.92, your answer will be wrong. It is not like that. So there is always a band in the answer. It's just like, you get a band in any gate examination questions, or like, or a JE,
Okay.
or just like a JE exam. So it's a band that will be given, and that band is sufficiently large that, okay, if you use any device and you do the methodology correctly and you substitute the values correctly, your answer will always lie in this band. Rest assured, like, your answer will always be there. So you don't need to worry about the nuances of the decimals. But if you do it correctly, then rest assured, like, they provide a good band of this answer, and you don't need to worry about this, like, on the
Sure, sure.
decimal aspect. Yeah.
Thank you,
But
sir.
yeah, but even if you, let's say, you get an answer, and by any chance, I mean, they are just said by people, like me or like any other students. I mean, like any other PhD student, as you being a PhD student, you will also understand that. So there might be a possibility that your answer might be correct, and by some and by an human error, the one who sets the the question might have given the wrong answer, for instance. In that case, what you can do is you can write the thing in the discussion forum, and instantly, I mean, not just, I mean, it instantly means not just in a minute or so, but at least in a day, or like or in a week, someone will review your, will review your I mean, your question, and then someone will again solve in, sit down and solve that, and then again, if the answer is wrong, then we will come up with the fact that okay, this answer is wrong, and you will be given marks based on whatever decisions the assignment team basically takes. Okay, so it's not that if you so there is the, so it's an open-ended thing that I'm saying, that if you feel that your answer is correct, but the answers that they say is wrong, or it might also happen that the options that you get might not have the correct answer, you can always write that so for a time being, you can mark one answer, then write it in the discussion forum, and then there will be a review on this, and if your if your opinion is indeed right, you will be given marks irrespective of it being a wrong or a right answer, and the error will always be rectified. That's the thing that we follow generally in any courses.
Sir,
Okay. Yeah.
once after the assignment, that solution will be, sorry, result will be published. Is
Yes.
it possible to share the solution from your side for the problematic?
So here's the thing. So all the solutions. Actually, my task is not to provide the answers to all the solutions that are there in the assignment. So what they do
Okay.
is the answers will be provided. Typically after, let's say, 3-4 weeks, after 3-4 weeks assignments have passed, you will get the answer key to all the previous assignments that you have just solved. Okay, but
Okay.
specifically, if you want to discuss any questions, you can always tell me, and then I'll have to go. For instance, if you today is so for instance, like if there is a question on assignment 1, and you tell me today that okay, I'm facing doubt in this question, instantly, like since I have planned something, I may not give the exact answer that you're kind of looking for. Of course, I will try to my end, but so what I will do is I will then, in the next class, before starting the discussion of the next class, I will come back with the answer for this, and I'll clarify on whatever doubts you are facing in that week's in that week's constant, before starting something new. That's the pathway we kind of follow. So is it okay on
Yeah.
that?
Yeah. Thank you, sir.
Yeah, yeah, all right. Okay. Yeah, any other questions? Okay, just a general announcement. So this session is recorded, so you can also watch this. So for all the viewers, this you can also watch this session. So this will be posted in YouTube, so you can also watch this at your end. And then while watching, if you are facing any doubt, please post it in the discussion forum for the ease of for the ease of us to know that okay, like these are the things that you are basically struggling with, or clarity needs to be provided. Okay, so please do that. And with that, let's get started. So today the agenda is basically on two topics, which are the contents of assignment 1, as you all know. So we will be starting off with something which is known as the Reynolds transport theorem, and also something which we all know is the basic definition of fluid dynamics, and we will see by what this basic definition means. These are just that things like the continuity equation, the mass conservation, and all those things that you basically saw it in the week's lecture. Okay, so we will begin by solving two problems precisely on Reynolds transport theorem, and we will see, like, it's not so just keep in mind that even if this is a problem solving session, we will frequently visit the theories, just that it helps you to revise what you had basically saw in the week session. And then while you are solving the assignment, okay, so these are the things that you can again recollect, that okay, this is something that we saw, and this could be the potential answer to this question. So that's the reason why we will be revising the we will not derive all the equations, because that is not a part of this live session. But we will, so whenever it is possible, given the time that we have, we will also back and forth, go back to the theory, and then come back to the potential questions that we are solving. Okay, so with that, let's get started. So So we'll start off by solving a problem on the Reynolds transport theorem, as you know. So I hope you are aware with what the Reynolds transport theorem is. So we and if you, and even if you are facing some doubt, we will start from the scratch and help you understand what exactly is by the Reynolds transport theorem and how can you use the Reynolds transport theorem to basically solve some things that we will see very shortly. Okay, but before that, let me clarify you the problem that we are trying to solve. So I call this problem basically to evaluate the change in water height of an inflowing tank, where as the name suggests, you can see that there is a solid tank where we have some fluid with density rho w. You can interpret this fluid to be water, so I wrote its density to be rho water. And then in this tank there are two pipes through which fluid is flowing in from these two directions. And without the loss of generality, what I consider is I can consider this axis to be my x-axis and the other axis to be my y-axis. So before using Reynolds transport theorem, you need to be very aware of the fact that what so on which axis system you're working on. Generally we'll be dealing with Cartesian coordinate system, but you must be clarified with it. For instance, this is a Cartesian coordinate that we are dealing with. It's just an xyz. So the unit vectors are there, ex, uy, and uz, which are Cartesian unit vectors. Okay, so you need to be be mindful of this fact, and then you do the analysis that we will subsequently see. Okay, so I think the question is clear. So we have a tank and we have water, and in order to fill this tank we have water flowing in from these directions. Okay, and this horizontal direction I call it the x direction, and the perpendicular direction is my y direction. So the z direction is the plane that is perpendicular to this x. So z direction is basically the unit vector that is perpendicular to this xy plane. I hope you can realize on it. So having said that, what they're asking is they're asking me what is the rate at which this water height, which is denoted by h, will basically change with time, or mathematically they are just asking me what is dh by dt, because you can appreciate that since the water is just flowing in, the height of the water level of this tank, which is denoted by h, will change with time, meaning that this is not a steady problem that we are kind of discussing. Okay, so having said that, they're just asking me what is the value of this h of t, given that the total height of the tank is h, and needless to say, of course, the water will keep on filling, okay, such till this h is less than the capital H, which is the height of tank. And we are looking in a scenario where this h is indeed less than h, such that the spillage of water and the backflow of water, because of the fact that water has been filled and all those things, are not of our concern in this problem. Okay, I hope the problem statement is clear. And before solving it, I will again wait for a couple of minutes for you to basically look at the problem, and then uh, come up with possible strategies. And as I said, we'll be using the Reynolds transport theorem. This is a very easy and a very preliminary problem, and it is so one of such problem is there in your assignment. The only complexity that problem carries is that we will basically see that here these velocities, as you can see, this v1 and v2, and we will discuss these things very shortly, what is the consequences of these things. But you can assume that this v1 and v2, which are fluid velocities that are coming in, these are constants. Okay, meaning that in principle, if you look, so if you basically zoom, so here is something that I would like to clarify before going into the solution, and I want you to listen to this very carefully. So if you zoom into this session of the pipe, I mean not session, the section of the pipe, you can see that the pipe is basically something like this, the inflow pipe that I'm considering. Okay, so in principle, that the velocity profile in, let's say, a circular or a plane channel, that the velocity profile is essentially parabolic in steady state. That is something in steady state. And all those assumptions that the flow is unidirectional, and we will see these things when we will be solving velocity profile. But at least you must have the idea that if there is a pipe, it may be a circular pipe, it may be a channel. And if we look into the fact that it's a steady flow, the flow is something which we will see, it's called a fully developed condition. We will see all these things. But in this scenario, the velocity profile is is essentially parabolic. But which means that the actual velocity profile will be something like this in the pipe. So it's just a parabolic profile. Okay, but for the simplicity of this analysis, and of course it is parabolic because it has to satisfy something which is known as no slip boundary conditions at the wall. because of the fact that the fluid is viscous in nature and all those things. We will see all these things when we'll go into solving the Navier-Stokes equation in the subsequent week. But it's just an idea that I'm giving to you. So please bear with me in this respect. But the thing is, the actual velocity profile is something like this, and it is a parabolic velocity profile with the certain assumptions that I have just now stated. But for the simplicity of this analysis, what we will do is, instead of assuming this velocity profile to be parabolic, we will assume that this profile is a constant velocity profile, and it is just an assumption that that we are taking, that this v1 and v2, instead of it being a parabolic, it is just constant. Okay, so this is actually, you can say, v2 actual, and this is what the v2 that we will follow in this question. So this is a means of simplifying your analysis of this Reynolds transport theorem. Okay, so this is the meaning when I say that v1 and v2 is essentially constant. Okay, so given this thing, we just need to evaluate that what is this dh, sorry, what is the rate at which the water level in the tank is rising. Okay, so this is the thing that I want to convey. I'll wait here for a couple of minutes, and then we will start off by applying by writing essentially the Reynolds transport theorem. We will see what Reynolds transport theorem essentially means, and then we will be solving the problem. Okay, and then I'll also discuss like a similar problem is there in your assignment, and what is actually the difference between the problem that you basically got in your I mean, what is actually the problem that is different from this to the one that you got in your assignment. Okay, uh, but before that, if you have any doubts on this, you can let me know. And just to clarify, this rho a is the density of air that is sitting atop this water surface. Okay, because this just can't be vacuum. Okay, so above this water, so long as this water level is rising, there is also air that is being sitting atop this vacuum. Okay, but we will see shortly that this air indeed doesn't play any role in the rate of change of this water height. All right, if no doubts, then let us begin by trying to solve this problem. So any idea that you want to say that how can we approach this problem? All right, I mean, please feel free to speak up, like if you wish to, that you want to share something, or you want to devise a strategy on how to solve this problem and things like that. Please, I mean, I expect that you will speak up, and also like you will keep this thing in an interactive way. Okay, so having said that, let's begin by trying to solve this problem. So since this is the first class, I'll go very slow. I'll cover each and every little details of different aspects that we will see. But as and when, of course, the course progresses, things should be faster, and I expect that these things, and I expect that the things that we do in the previous weeks, that we will see later on, are the things that you basically know, and then it helps me to take the new things, to bring up with new things, uh, having understood the previous ones crystal clearly. Okay, that is something that I expect. So so let's just begin. So what we will do is, the very first step, you know for using the Reynolds transport theorem, is the choice of something which we call as a control volume. Okay, so what we will do is, we'll begin by first drawing the control volume. So the control volume is something, it's just a space, so it's just a fixed space that we are looking at in something which is known as the Eulerian approach. Okay, so in this case, the control volume that we'll be choosing is basically, this volume of water. Okay, that is essentially rising in the tank. Okay, and this is precisely my control volume. So the very first step, okay, of applying Reynolds transport theorem is to first identify what control volume you are kind of dealing with. Okay, now some may say that I can also choose this volume of water and the volume of air to be my control volume. And this is also fine. And you can prove that if you, so the choice of a control volume is always in the hand, so it's always in our hands, okay? And irrespective of the choice of the control volume, our answer is always invariant. That you cannot say that, okay, I choose a different control volume and some other people choose a different control volume, so we'll get different answer. It's nothing like that. And you can indeed show that if someone else choose a control volume which contains the water mass and the air mass, still your dHdt will always be the same, because that is an invariant with the choice of control volume that we have. Okay, so this is something that again I would like to clarify. So the first step is choosing the control volume, and now as a choice I choose this water mass to be my control volume. Okay, and and as a homework I will encourage you to to repeat this, to repeat the same problem by choosing this air mass as my control volume, sorry, choosing the air mass and the water mass to be my control volume, meaning that what will happen if I choose the entire tank as my control volume is something that I would encourage you to do it at your end. Okay, all right. So once we choose this control volume, we will now apply RTT. Now can you tell me, for calculating this dHdt, okay, what conservation should we look for? I mean, so RTT is basically a conservation of things that we are doing it. Okay, so we will see once we write the RTT, we will see that, or that so we will see that what conservation are we essentially doing it. But can you just suggest me that what should be conserved here, in order to come up with a solution of this DHGT? Can you give it a try? So what conservation principle should we use in the RTT, in the Reynolds transport theorem, to basically evaluate this rate of change of height of the water? Okay, so try to think of something like this. Okay, so what is essentially happening is there is a water stream that is coming in, there is a water stream that is coming in, and there is there and because of these inflowing streams, there is water which is getting accumulated in the tank. So it's like, if I apply the mass conservation, it's like there is a mass flow rate or a mass coming in, and there is in from two direction, and due to which there is mass accumulation that is being taking place inside this control volume. So what we will do is, since we are talking about masses, this means we must apply RTT, which governs the mass conservation basically. Okay, so this is something that we'll do. So we'll apply RTT, and RTT is the short form of Reynolds transport theorem. I think you guys know by it now, for mass conservation. Okay, and where we are applying this mass conservation, we are applying this mass conservation in this chosen control volume. Okay, so we apply RTT for mass conservation in the control volume, and I'll denote the control volume as CB. Okay, so if we do that, let's now write down the Reynolds transport theorem, and then we will see the nuances of it. Okay, so if I have any property in any, so if I have an extensive property n, this n could be an extensive property. I think you know what is an extensive and an intensive property by now. So this n is an extensive property. So extensive properties are properties which depends on mass basically. That's the simplest thing that you can say. Then for any extensive property, we can define an intensive property, which I will call it as eta. So eta is my intensive, property. And the relation between eta and n is straightforward. Eta is just, n by m. That is, you are calculating where m is basically the mass. So every property, if you divide it by its mass, it becomes an intensive property. Okay. So for these two properties, if I apply the Reynolds transport theorem, okay, then in general it becomes dn dt, which is the rate of change of the extensive property, but this is calculated in something which is known as a control mass system. Okay, and this is equal to the rate at which the property changes inside the control volume, and it is denoted by del t of integral over the volume rho, which is its density, times eta times dv, where this v will so in this course we will denote volume by this v, not by this v, because we generally denote the the usual small v as a velocity in fluid dynamics. So we will denote this v with a cut as a volume and not velocity. So these things need to be clarified. So so this term that you see on the right hand side is nothing but the rate at which the property per unit mass, which is eta, changes with time inside the control volume, plus there is a correction term which we call it as the efflux, which is the control surface integral of rho eta, the velocity dot n cap dA. So that's it. That's the Reynolds transport theorem. So this is the, you know, so this is basically the Reynolds transport theorem that you have seen it in the lecture series as well. So since you have already derived this in the lecture series, we will not go into the derivation of this, but this is basically the Reynolds transport theorem. Okay, so I'll repeat. So this term speaks about how my extensive property changes inside a control mass system. I think you, at least you know what is a control mass system and a control volume system. Okay, so so this is something that that at least you should be so it's it being a, you know, it being a under, so this course is typically a postgraduate level course. So since I expect that at least by now you know what is a, you know, what is a control mass system and a control volume system. Okay, so if not, it's completely fine. I can explain it, but please let me know that if it is required or not. Okay, and and I'll be happy to clarify it. Okay, but I believe that you know this by now, that what is the difference between a control mass system and a control volume system. Okay, so what the Reynolds transport theorem says that how the extensive property changes inside a control mass system. This is how it is linked basically to the control volume system, which we denote it by the right hand side of Reynolds transport theorem. So this term, okay, so this term that you see, that is the del del t, okay, of integral over the volume, the density times eta, which is the property times unit mass, multiplied by the differential volume. So this term is something, so this denotes, I'll write it down, rate of change of, you know, so it's basically the rate of change of the property inside the control volume. So it is basically the rate of change of property inside the control volume. And this term that you see, so this is a surface integral term. So you can appreciate that this is the volume integral and this is the surface integral. So volume integral means we are dealing in terms which is inside the bulk of the control volume, and this is a surface integral. So this is basically the efflux term. And in true sense, it is actually the net efflux. It is more accurate to write it as a net efflux. So I think this is clear to you. Okay, what different terms inside the Reynolds transport theorem means. So you have one question in your assignment, so as to what Reynolds transport theorem usually does. So you can appreciate that there are a couple of things that you can admire from the form of the Reynolds transport theorem that we deal with. Okay, the first thing, it is a bridge, or it is a connection between a control mass system and a control volume system. Okay, the second thing, a control mass system is a Lagrangian, so it's a Lagrangian definition. So do you know what's the difference between an Eulerian and a Lagrangian definition? Can you tell it with a yes or a no? And I have one problem where essentially the difference between an Eulerian and a Lagrangian, you know, description will be clarified. But at least, do you know what what is meant by a Lagrangian system and an Eulerian system? uh,
Lagrangian is a system approach. Eulerian is a control volume approach.
Eulerian is yeah, that is true. Yes, so that is true. That the Lagrangian is basically a control mass. So system means it's a control. It's a fixed mass system. That's I suppose that's what you are talking. And Eulerian means it's a fixed. It's like we are looking at a fixed space in a volume. So I think that is what you meant by. You are true, but that is essentially right. But to be more precise and to to have some good visualization, Lagrangian system means, for instance, let's say try to understand this. So let's say we are looking at a flow through a pipe. Okay, so there is a circular pipe and there is a flow that is coming. Forget about whether the flow is turbulent or laminar and things like that, but we are looking into this flow through a pipe. Now if I look from a system on which I'm focusing on each and every fluid particles, okay, and I want to track how an individual fluid particle move inside the space, that is a Lagrangian approach. Okay, I repeat again, I hope this is clear, that let's say I'm looking at a flow through a pipe, there is flow of water that is flowing. Now if I concentrate on just one fluid particle, okay, just one fluid particle in the host, in the whole vast of in the whole, I mean in the whole fluid, if I just concentrate on just one fluid particle and I just track how this single fluid particle that I concentrate on basically moves with time, it becomes a Lagrangian system. Okay, on the other hand, instead of just focusing on just one fluid particle, okay, if I concentrate on a fixed space of the pipe, let's say for instance I'm looking at section A and section B between the pipe, and now instead of focusing just on one particle, if I focus on a fixed area or a fixed volume, I would say it's not an area, it's a volume. If I focus on a fixed volume and I don't care about how many, which particle basically comes in and which particle basically goes out, that is none of my business. Okay, I just look into a fixed volume and I see that how many particles are there in that fixed volume. I'm sorry, I meant to say, I want to see that how the particles in the fixed volume is basically behaving. Okay, so if I fix my region in space, it becomes an Eulerian approach. Okay, so this is essentially the two difference between, so precisely the one that you said is correct, and this is a more fundamental difference between a Lagrangian system and an Eulerian system. A Lagrangian system is where I focus on just one fluid particle. An Eulerian system is where I don't instead of focusing on just one fluid particle, I fix my space, I fix my point, and then I try to see how many fluid particles comes in, how many fluid particle goes out, or things like that. Okay, so that is the difference between Lagrangian and Eulerian. And Reynolds transfer theorem is essentially, it's a connection or a bridge between a Lagrangian approach, which is typically the left hand side of the Reynolds transfer theorem, because you can see this is this says that in a control mass system how the property changes with time, which means that I am just looking into one fixed particle, and I'm seeing the property of that particle, and that's why it becomes a control, it becomes a control mass system. So this is a Lagrangian description, and the right hand side of Reynolds transfer theorem, as you can see, you can appreciate that if you just look at it closely, it's an Eulerian description. So a Reynolds transfer theorem is a bridge between a Lagrange. So we are writing equations in Lagrangian system, and then we are connecting it to Eulerian system. That's what we are doing. Now, the essential curiosity that should come into your mind is that why are we doing this? So why don't we just solve it in the Lagrangian frame? Why are we interested in this Eulerian frame? That is the curiosity that should strike your mind. The reason why we are doing is, in fluid mechanics, since there is not just one particle, for instance in a pipe flow there are millions and billions of fluid particles that basically basically travel. At least you just pick a 1 meter pipe, okay, and then just make water flow through it. There are millions of particles that will basically flow through the pipe. Okay, which means you will require very very high computational resource if you follow a Lagrangian coordinate and solve for whatever you want to for all the fluid particles, because you need to first identify one fluid particle, track its dynamics, and then repeat it for all the fluid particles. Okay, so in fluid mechanics, Lagrangian, in unless and until there are some benefits, it is more, what I would say, it is more convenient to deal in this Eulerian approach, because in Eulerian approach we don't bother about single particles, we just fix the space. Okay, but the laws of nature, for instance the Newton's laws of motion, for instance the first law, second law, third law, these are all written in Lagrangian code, in Lagrangian description. Okay, for instance F equal to ma is not written in Eulerian description, it is written in Lagrangian description. Okay, and 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 basically the Navier-Stokes equation that you write is an Eulerian description of basically the second law of Newton. Okay, so the idea is, since we have equations written, since the equation of natures are written in Lagrangian description, okay, and it is more what to say, customary and easy to deal fluid mechanics problems in Eulerian description. That's why we need a bridge which connects, the laws of nature with the equations that we tend to solve in a fixed defined space in fluid mechanics. So that's why we have this Reynolds transport theorem, which basically acts as a bridge between these two concepts. We have the equations in Lagrangian frame. We want to use them in Eulerian frame because they are easier to deal with. Okay, and that's why we have this bridge, which is nothing but the Reynolds transport theorem. Okay, so that is something that that you must try to appreciate. Why are we using this Reynolds transport theorem? All right, so that's the idea behind it. So let's now use this. So let's now use this and try to find out what will be this DSDT. Okay, so now can you tell me, if I use this Reynolds transport theorem for mass conservation, what will N become? That's simple, right? Since we are dealing with mass conservation, your N is just mass, which means the eta, which is N by M, is just 1. Okay, and then if we just apply, what we will get is, let's just substitute this into the Reynolds transport theorem, which is basically this. What we will get is rate of change of mass inside a control mass surface, which we call as a control, which also we call as a control system that you just said, and this is equal to the rate at which the property changes inside the control volume. So now my eta becomes equals to 1. So that's why we'll just have a 1 here. So it is just rho times dV plus the efflux. So it is so this means that I am doing a closed surface integration over the entire surface. Okay, so this closed thing will denote it as a circle in an integral. I hope you are familiar with it, and it just becomes rho times v dot n cap dA, where this v is basically the velocity at which the mass gets entered inside the control volume, and n cap is the unit normal of the area that we choose. Okay, for instance, if I have an area something like this, if I have an area, so let's say this is my control volume. This is basically my control volume. Okay, and this is my control surface, the lines, and the blue line is my control surface, let's say. So this is my control surface. So n cap is the unit normal of this control surface. This is something that you need to realize. Okay, all right. I hope so far you are with me on this. Okay, so now can you tell me, what is this term? What is the rate of change of mass inside a control system? So what is the very definition of a control system? The definition of a control system is that mass cannot enter, so it's like energy, there can be energy interactions inside the control system, but mass cannot enter in and out of the control system, which means the rate of, irrespective of the, please keep in mind, this can happen in a control volume, but this cannot take place in a control system. Okay, so irrespective of whatever problem you are dealing with, the rate of change of mass in a control system is always equal to 0. And this is not the case in Eulerian description, but this is the case in Lagrangian description in a control mass system. That's why it has got the name control mass system, which means your mass will always remain fixed inside your system. Okay, so this means this term is always equal to 0. Okay, so we are just left with this left hand side being equal to 0. Okay, so what we will do is, we'll assume that my density, that is so this is basically rho w. So this is rho w, which is which is the density of water that we are basically looking at. So this rho w is so it's the density of water. Okay, and we'll assume that this rho w, which is the density of water, is constant, meaning that I can take this density outside these integrals. Okay, which means I have now 0 equal to rho w del t of integral over the control volume dv plus rho w integral over the control surface v dot n hat d. I hope you are with me on this so far. Please let me know if you have any doubts on this aspect. Okay. So did you understand up to this point? Like, can you just give me with a yes or a no? Because I don't. So it being an online session, I can't see that whether you are, you know, kind of understanding this or not. So
Yes, sir. Yes, sir.
yeah,
I mean,
yeah,
we are
exactly.
understanding.
Yeah, exactly. Thank you very much. Thank you. So now what we can do is, since this density is constant, I can simply strike out rho w, because rho w cannot be equals to 0. So I can take rho w common, and this means that this so I can just simply strike out, because the left hand side is just equals to 0, which means I am now just left with rho, sorry, 0 equal to del t of integral over the control volume. Remember, this control volume is this control volume that I am considering in space. You should always, keep this in mind when you are, applying the Reynolds transport theorem. So this is del t of rho of integral over v dv plus the integral over the control surface v dot n hat dA. Okay. Now we will look into these terms very specifically. Okay, the first term says is that you pick a differential volume inside the control volume and then integrate it of the differential volume. For instance, if I so for instance, if you have a close look into this control volume, if I pick, a generic h, okay, at some location, let's say, the dv, the differential control volume, is nothing but, so for this generic h, the differential control volume, as you can see from this figure, of course this will also, continue in so I'm considering a unit width. You should appreciate that. So the differential control volume, as I was saying, so so this red slab basically happens to be my differential control volume. Okay, so dv, if you guys, so if you just pay a little bit of attention, this integral of over the volume, this dv, this simply boils down to the area of the tank time h of t. Did you understand this or not? This is typically because, this is typically that is okay. I'll just prove it for you. This is a very simple thing, but yet I'll prove it for you, because of the fact that it's just the first sum that you are solving. So it's like I am first considering, so I'm considering a generic height h, and I'm considering a slab which have a thickness of dh. Okay, and of course this area, as you can see, I mean the figure is little bit becoming pesky, but like the area, as you can appreciate, is 80, and the area of the tank is not changing. Remember that, which means this integral of dv, so this can be written as integral over the volume. Dv is your 80 times dh. Okay, and this integral will just now simplifies to integral from 0 to h of t. At will come outside the integral because of the fact that your area of the tank is constant, and dh, which is nothing but your at times h of t. This is only because the area of the tank, okay, the cross sectional, you can say it's a cross sectional area of the tank, it is constant. Only the height of the water in the lateral direction is just changing, and that's why this integral over dv simply boils down to the area of the tank times h of t, which means the first term just simplifies to del t of at h of t, and since area of the tank is a constant, it is also not changing with time, I can just simply write it as at times dh of t by dt, which means the partial derivative with respect to time simply get transformed to an ordinary differential of dh dt. That is only because the height of water is just a function of time, it is not a function of space. Okay, I hope you are clear on this aspect, that why this term, so this simple term boils down to just this term. Okay, and I hope you understand how we got this step, how we got this step from this point. I hope I'm clear on this. Please let me know if I need to explain it again or there are some
Yeah.
clarifications.
Yes,
Yeah,
sir.
yeah,
Yes,
you
sir.
can.
We are clear.
You want me to you want me to repeat it?
No, sir. You
Oh,
can
okay.
continue.
Yeah, yeah. Okay. Thank you very much. Yeah. So, okay. So the first term is now done. So the first term just simplifies to 80 times dsdt. Okay. And just for the ones who joined late, we are just dealing with the first problem only. So we are basically just, solving a problem where we are supposed to calculate that if there is inflow water coming from these two sides, what is the rate at which the height of this water would basically, change with time. That's the thing that we are kind of calculating. And we are applying the Reynolds transfer theorem using mass conservation to basically solve this problem. Okay. So that's the brief thing summary that I can just give now at this point of time. But yeah, so if I now solve the second term, we have, so the second term is a bit tricky. Okay, and I'll tell you why. So the second term, as you can see, is basically this term. It's integral. It's a closed surface integral of the control surface rho v dot n hat. So okay, I don't have the rho because rho is just cancelled out. So I'll just omit the rho. So it is just v dot n hat dA. All right. And this is where actually you need to have a close look into the inflow systems that are coming inside the tank. Because since this is a surface thing that we are calculating, we must look at what is the mass that is coming out in the control volume from the surfaces. Okay. So these terms, this v dot n hat dA, what I can write down is, please let me know like if you understand this or not. So this v dot n hat dA, this can be written as this term can be written as integral from surface 1. See how many, so let's have a look at the control volume and try to understand one thing. So there is only two possibilities, there is only two surfaces through which mass is coming inside the control volume. Okay, for instance, this is, so if I fix this control volume, okay, in this control volume only these and these surfaces are the part where mass is basically coming in. This means there is actually a flow of mass inside the control volume which is coming with some velocity v. Okay, and all other remaining surfaces, for instance this and this, okay, the velocity is actually zero, which means the efflux, I am only bothered in the efflux term for the surface 1 and the surface 2 only. That's it. Because I know that for all the remaining surfaces, if I stitch together, the velocity is just zero, because there is no mass coming in from the remaining part of the surface of the control volume. Okay, which means I can write down this surface term, that is closed surface integral of v dot dA for all the surface as integral for surface 1 v dot n hat dA plus the integral of surface 2 v dot n hat dA. Okay, and I am doing this for surface 1 and surface 2. I hope this is clear to you. Okay, now here is the thing that I was saying, that what is the consequence of choosing the inflow velocities to be constant. Okay, so now as you can appreciate that if my if my velocity v at the surfaces 1 and 2, if my velocity v at the surfaces 1 and 2 are not constant, then then basically, for instance, if I have a parabolic profile of this sort, I must integrate velocity along the surface when I do this surface integration. Okay, for instance, this surface integration is what it's so I can write this surface integration as an integration over integration over y, because your width is constant, some velocity which is a function of y dot n hat dA. Okay, but since my velocity is constant and it is not a function of y, I can simply take this velocity out, v dot n hat, outside the integral. That is only because I have assumed in the first place that my velocities are constant. If it is not constant, you cannot take v dot n hat outside the integral, and you have to do the integral basically to to deal with the variation in the velocity in the y direction that we are considering. For instance, if I have a velocity profile of this form, then this integral over the surface v dot n hat needs to be carried out, and you cannot take velocity outside the integral. You basically need to do the integration. That's the only thing that you need to do. So in one of your problem in the assignment, one of the velocity profile is constant and the other velocity profile is parabolic in nature, which means you need to basically integrate the velocity profile to basically come up with the inflow flux that is coming out inside the control volume. Okay, that integration is just an integration in y, for instance, in this case. Okay, for example, if I have a parabolic velocity profile, let's say, I just have to integrate it. I just have to do this integration of u1y dy. That's the integration that I need to do. from, from here to basically the height of the channel. But luckily for this question, since I have a constant velocity profile, I can take this v dot n hat, okay? I can take this v dot n hat outside the integral, which means this simplifies to v dot n hat, okay, written for surface 1. Because of the fact that your velocity is constant, I can take this outside the integral, okay? And this is integral over s1 dA plus v dot n hat written for surface 2 integral over s2 dA. Okay. All right. Now, can you tell me, based on this figure, I expect an answer from this. Can you tell me what is v dot n hat for surface 1? Can you tell me? My question is, what is this? Where I repeat, n hat is the unit normal of the control surface, and my control surface is is this. These two are the control surface. Okay. You can give it a try, or I'll be happy to explain you this concept. This is a very fundamental concept in Reynolds transfer theorem, which people tend to ignore, but it is very detrimental. And you will see that if you just ignore this, you will end up getting the wrong answer, because your signs, that is the plus and the minus sign that you basically do, that will change, and this will give you wrong answer in the final result. Okay, that's why we will spend some time on this. Okay. All right. So this v dot n hat for surface 1, see, I'll explain it here. So this v dot n hat for surface 1 can be written as, let's say, v1, which is the component of velocity of, let's say, so this is, so understand that v here is a vector. I am writing v for surface 1 as v1 ex. Why ex? Because my ex is the unit normal in the x direction, and since my velocity is just unidirectional in the x direction, I can write v1 this. So I can basically write this v1, the vector v1, as its magnitude times ex. Okay, but the n hat, which is the unit normal, is in the negative x direction. It is not in the positive x direction, because if I choose this surface, a unit normal, okay, and unit normal is generally denoted outward of a surface, which means that if I choose a surface, my n hat for surface 1 is minus ex, where ex is the unit vector in the x direction. I repeat, since although my velocity is in the positive x direction, that's why I write it as v1 ex, where ex is the unit normal in the x direction. My unit normal for the surface, for this surface, is in the negative x direction. That's why n hat for surface 1 is just minus ex. Okay, I hope this is clear to your end. That is again because an unit normal is always directed outward, and the outward unit normal is always in this direction, and that is why I always say, please consider your axis system before doing sums on Reynolds transport theorem. All right, so that means that this dot product is now needed to be done with minus ex, basically, because n hat is minus ex for surface 1, which means an ex dot ex is just 1. Okay, the dot product of an unit vector with itself is just 1, and you know that, which means this just boils down to minus v1. Okay, similarly, can you tell me what is this v dot n hat for surface 2? Can you tell me just by looking at this figure, based on the explanation that I gave for surface 1? Can you tell me what is v dot n hat for surface 2, where the direction of velocity for surface 2 is in this direction?
It's V2.
Yeah, v2, but in this form, can you tell me, in this form, that is, the magnitude is v2, and what is the direction? Is it plus ex or minus ex? See, ex is in this
It
direction. Yeah.
out my mm,
Yes,
um
you were correct. It's minus ex basically. Why? Because see, ex is the unit vector in the positive x direction. Ex is basically in this direction. Okay, and its velocity is in this direction, which means the direction of this velocity is in the negative x direction, and that's why v2 is minus of the magnitude times ex. You understand this?
yes.
Exactly. Which means this term is now minus v2 ex dot. Now, can you tell me what is n hat for surface 2? Is it plus Ex or minus Ex? What is n hat for surface 2? Remember, n hat is always outward of these surfaces. Okay? N hat is always outward of these surfaces. What is n hat for this surface? Is it plus Ex or minus Ex?
Here it is plus Ex.
Exactly, it is plus Ex. Why? Because this is my surface, this is my second surface, and n hat is basically in this direction, which is in the plus X direction. Which means this is dot product with Ex. And this just boils down to minus V2. That's it. So this this surface integral, this surface integral essentially becomes, so the closed surface integral of v dot n hat dA is just minus v1 integral, and this remember these integrations are there, so it is integral over surface 1 dA1 and minus v2 integral over surface 2 dA2. And what is this integral? See, the area of the surfaces is just constant. I just stated in the question that these surfaces, the surfaces has just got an area A1. Okay? Which means this integral of a differential area of surface 1 over the entire surface S1 is just, so it is just A1. That's it. Because my area is constant, that's a one way of saying it. And this just boils down to A2. Which means it, so the surface integral term, that is the efflux term, is nothing but just V1 times A1 minus V2 times A2. That's it. Which now means if I just now stick around this term, so I have evaluated this term, I have evaluated this term, and if I just combine this term to basically substitute here, basically, substitute it in equation, let's say 1, I just get, what? So I just get AT times H of T minus, sorry, not H of T, it is dH dt. dH dt. Okay, that is typically because this term comes from this term. So this is basically what is this that we have just now saw. Okay, so it is AT times dH dt, and then I have the efflux term, which is minus V1 A1 minus V2 A2, and this is equals to 0. Which means all I just require is to calculate this dH dt, and this dH dt just comes out to be V1 A1 plus V2 A2 divided by AT. That's it. That is precisely what the rate of change of the water height with respect to, you know, with respect to with respect to time would be. Can you tell me, by looking at this expression, is the rate of change of water height with respect to time, that is dH dt, a constant or a variable? Given all those things that I already said you, that is V1, V1 A1, V2 A2 and AT. Is it a constant or a variable? Can you give it a try? That is dH dt a constant, or it is just some function of time or some function of other things? See, it's a constant, right? That is typically because this v1 is just the constant velocity with which water is flowing in, that I have already stated. A1 is the cross sectional area of the section A1. Similarly, this v2 A2 is the exact same consequence what I said in 1, and area of the tank is also a constant, which means in this inflowing tank, okay, the water height will rise in a constant manner. Okay, I am not saying h of t is constant. I am saying that the rate at which h of t increases with time is basically a constant. Which means if you, so this is a constant. So you can so what you can do is you can also integrate this, and you can show that h of t is essentially a linear function of t. That is, your height will increase linearly with time, based on the physical paradigm that we have just now solved. Okay, I hope this is clear to you, why I just said this. Okay, so that's it, guys. That's the first answer that we just now evaluated by using the Reynolds transport theorem for mass conservation. I'll stop here for a couple of minutes. If you have any questions, you can ask me. All right. If no questions, I hope you understood this, and I hope you appreciated like how little. So it's simple problem, yet it has very little nuances. For instance, what happens when the velocity profile varies? So you have a question on assignments. You try this question. If you have any doubts, please post it in the discussion forum, and I'll clarify this in the next class. But give it a try, okay? But you can see the little nuances of the unit vectors, the direction of the unit vectors, and the velocity vector, and the idea of a control volume, okay, and then how to apply basically Reynolds transport theorem, and what does Reynolds transport theorem essentially does. So it's a bridge between a Lagrangian or an Eulerian approach, or it's a bridge between a control system and a control volume. It's kind of like that, okay? All right. So with this, we finish the first problem. I also have a second problem on Reynolds transport theorem, but I'll not discuss this problem now given the time, time that we have. But I'll post the solution of this problem in the discussion forum if you are interested. But we'll do a different problem now. Is that we will look into something which is known as stream function, and we'll through a problem we'll appreciate the meaning of stream function, and and we will see that what does stream functions or something which is known as streamlines essentially means, and you will indeed see that these have indeed very important mathematical consequences apart from their physical relevance, okay? All right, so the question is like that: you are given a flow field. Can you tell me this flow field, that this is a velocity vector, and of course this velocity vector has two directions. In the x direction it is ax, in the y direction it is ay. That means ux, which is the component of this velocity field, in the x direction is just ax. Its component in the y direction is minus ay. This is given to you, where a is a constant. Its magnitude is there, as you can see. So this velocity field is given. You are asked to calculate the stream function psi. That is all that you need to do. But we will do that. We will do that shortly. But can you tell me that this velocity description, is it an Eulerian description or is it a Lagrangian description? Yes. Yeah.
I think this is a Lagrangian.
This is a Lagrangian. Okay. So what made you say it's a Lagrangian description? Can you uh, can you elaborate?
Um, Sorry, I didn't get it.
Okay. No, I'm asking. Yeah, I understand you said that it's a Lagrangian description, but can you like, I mean, what made you think that it's a Lagrangian description? Can you just elaborate? I mean, I'm just asking. It's just not a question, but I'm just asking that what made you think that it's a Lagrangian description? Can you throw some light on it, or else I'll clarify. I mean, it's completely fine. Actually, it is not a Lagrangian description. That's the reason why I asked you that what made you think it's a Lagrangian description. I'll tell you why it's not why it is not a Lagrangian description. See, when I say it's a Lagrangian description, in fact, we will solve one problem involving Eulerian and Lagrangian, and this should clarify your doubt. Okay, so I'll solve this problem, and if time permits, I'm planning to solve one more problem which should clarify your Eulerian and Lagrangian fields. Okay, but this is not a Lagrangian description, because see, again, as I said, let me give you this description. I think this would clarify things. Okay, see, I'll again go back to that pipe example. As I said, for instance, I'm looking at a pipe. This is just one, let's say, section of a pipe, and I have water flowing through this pipe. Okay, I have fluid basically flowing through a nice little laminar flow that is flowing from one section. Let's say I fix this section of the pipe. Let's say this is 1 and this is 2. Okay, this pipe is long, but I am just looking at these two sections. Okay, all right. Now imagine there is a fluid particles that is flowing. You see, the pipe doesn't end here. Okay, just let me clarify. This pipe is long. I'm just looking at a section 1 and 2 between the pipe. That's the thing. Okay, this pipe is infinitely, let's say, long in let's say the x direction. This is my x direction that I'm considering. So imagine now I'm just looking at a fluid particle that is flowing through this pipe. Okay, so when I just fix my attention to this fluid particle, okay, what information do I need? I just need that what is the position of this fluid particle. I'll call it as x bar of t, because position is, in general, the position we denote as a position vector, so I'll denote it as x bar of p or x bar of p. I just need to know what is the position of this particle at any given instant of time. Okay, because I'm just looking at just one fluid particle, all I need is I just need to know where this fluid particle is located in the pipe. Now if I know its position as a function of time, I also know its velocity, because velocity of this fluid particle, this, let's say I'm calling it as up, this is nothing but d of xp, which is a function of time by dt. Now, since the position is just a function of time, and this is sufficient for me to know what the velocity of the fluid particle is with respect, I mean, what is the velocity of the fluid particle if I differentiate this position with respect to time, meaning that I am just saying that all the variables, this x of p, this up, these are just functions of time in Lagrangian coordinates, because just by knowing at what time this single fluid particle is sufficient for me to calculate all the properties of this fluid particle. This velocity, if there is acceleration, and so on and so forth. Okay, which means if I have variables in Lagrangian frames, it will just be, it will just be temporarily varying. That is, they are just going to be functions of time. On the other hand, if I look at if I look at the space in the pipe instead of focusing on a single fluid particle, then if you ask me what is the velocity field, because in Eulerian description we talk in terms of fields. Then if you ask me what is the velocity field, then I would ask you, I will give you the velocity field, but you need to tell me which position do you require the velocity field. Then there comes the then there comes the definition of position. Now if I speak about position, this means that the velocity fields are a function of space also, not just time. They might be a function of time, but they also should be a function of space. Okay, which means in Eulerian description, my fields, for instance, if I describe a velocity field in Eulerian description, it will be a function of time, but it will also be a function of space. This x bar is nothing but x ex plus y ey plus z ez. I hope this is clear to you. Okay, it may or may, so there is something which is known as a steady flow. For steady flow, your velocity fields, your Eulerian fields are not a function of time, and this is indeed an example of an Eulerian steady flow where your velocity field is just a function of space. Because if you are talking about Eulerian description, you need to tell me, okay, what space are you looking at along with the time. Now this time will disappear if I am considering something which is known as steady flow, which means that all your velocities, all your variables, not just velocities, are independent of time. So are you clear now that what description is this? Is it an Eulerian or a Lagrangian then?
Eulerian.
Yes, exactly. This is an Eulerian description. So the stream, there is something called streamlines. There is something more complicated which is known as vortex lines. All those things are defined for Eulerian description only, remember. Okay, so this is an Eulerian description. Okay, now let's just go ahead and calculate the stream function. So as you know, so from this velocity field, I can write that my ux, what that is the x direction of velocity, is ax, and my uy is just minus ay. So as you know, the stream function we denote is generally by psi. This is my stream function. This is related to the velocities in this manner. So my ux is essentially del psi by del y. Okay, let's just substitute it, and then I'll tell you some very interesting features of stream function, and also something which is known as velocity potential function. Okay, so this so let's first just solve this sum, and then we will discuss this. Okay, so ux is nothing but ax, and this is just del psi by del y. So what do we now need to do in order to get psi? We just need to integrate it. It's a simple integration, right? So what we will do is del psi is just ax times del y, and then we'll integrate it. But remember, see, this psi in general, this is essentially a function of x and y, but we are doing an integration with respect to y only, which means when I do this integration, this psi becomes psi, which is a function of x and y. This integral is just with respect to y, so it just becomes axy, but there will be a constant which will be f of x. I hope you are aware with this mathematics, that in a variable which which is not an ordinary variable. So this psi is basically a function of two variables. When you are integrating with respect to one variable, the constant of integration is, so it appears to be a function of the other variable basically. I think you are aware with this. Okay, so the psi is axy plus f of x, but we are only asked to evaluate this psi. Okay, so is it, so are we done yet, or there is something that we need to do, that we still need to do? Because we are, so they just asked us to calculate this psi, right? And we just integrated and we told that psi is just axy. So are we done yet, or like there is still something that we still need to find out? See, knowingly or unknowingly, when we did this integration, we have, you know, so there is a function just that just popped up when we just did this integration, which is f of x. And this f of x is an arbitrary function we don't know, right? And we need to determine this arbitrary function. And for that, we'll take the help of the y direction velocity. Because if we calculate, let's say, v from this definition, if we calculate v from this definition of psi, as you know, v is nothing but minus del psi by del x. Okay, which means if I do this, it just becomes minus ay plus df of x by dx. Just differentiate this with respect to x. That's it. But from the question, we know that, okay, this v is actually uy. I'm sorry, the notation is uy. That is the y, is the y component of velocity, and y component of velocity is minus ay plus df of x by dx. But from the definition, I know that ui is just minus ay, which means if I compare this ui with the obtained ui from the stream function, if I compare it, can you comment what this df of x by dx should be? I repeat, we got ui as minus ay plus df of x by dy, and from the question, we know that ui is just minus ay. So can you tell me what is df of x by dy, df of x by dx then? Just by comparing this and this. Yes, can you tell me? Just a simple comparison, right? Ui from the question is minus ay. Ui that we got from the stream function is minus ay plus df of x by dx. So what should be the value of df of x by dx? I mean, it should be 0, right? It's a straightforward thing. Just so it's just a comparison, right? Ui is this. From the question, we got ui is this. So this means if we compare this, since the ui, so ui is just an ui, it's a fixed thing. It's just the y component of velocity, which means that this is basically 0. So by comparing, okay, df of x by dx is 0, and you just, if you simply integrate, f of x is just a constant, when we'll denote this constant by c1. So this means the complete streamline psi as a function of x and y is axy plus c1. That's it, where c1 is just an arbitrary constant, and by changing the value of c1, we will get a family, we'll get something which is known as a family of streamlines. Okay, and a family of streamline together is called a stream tube. And so for instance, if I choose c1 to be 1, I'll get a single streamline. If I choose c1 to be, let's say, a different value, I'll get a different streamline. It's something like that. So just to make things, just to make things, just to visualize things, what you can do is you can you can plot these streamlines in the xy space. And can you tell me what this plot would look like in the xy plane? If you plot this, can you tell me in the xy space?
So slope.
Slope. So if you, so I'm just asking, no, I'm just asking that what, so if I have a xy coordinate system, what would the plot of psi in this xy coordinate system would look like? I mean, I'm asking you to plot just psi, the nature of these streamlines. Slope is something that if I calculate d psi by, let's say, dx, I'm calculating slope with respect to x. This is something. The slope essentially will give you will give you the velocity. That's a different thing. So I'll come to that. That a tangent. So here a slope will essentially mean tangent, and a tangent to a streamline is will give you the instantaneous velocity. That we will see. And that also is a part of your assignment. But I'm asking you that can you plot these streamlines in this xy space? What would the plot look like? So can you tell me when x goes to infinity, what is the value of psi? When x goes to infinity, if I put this infinity, if I take this x to be infinity, what is psi?
That also goes to infinity.
Yeah, exactly. That's a straightforward thing, right? So psi will go to infinity, means it will be somewhere here. When x goes to infinity, okay, generally we take this Generally, we take this as y, we take this as x. So I say that when x goes to infinity, your psi will also go to infinity. Similarly, when y goes to infinity, your psi will also, go to infinity. Which means that these lines should look something like this. Okay? It goes to infinity. When y goes to infinity, it goes to infinity when x goes to infinity. So this is one streamline for a particular value of C1. Let's say if I choose a different value of C1, I will get a different streamline, something like this. All of this will go to infinity when x and y go to infinity. Let's say this is for some, let's say C1, 1. Let's say this is for some, let's say C1, 0. These are different values of this constant, that's it. A different streamline, an other streamline would look something like this. Let's say this is for some C1, 2. Okay? So all these streamlines, you know, are together known as stream tubes. Now, always remember that if you pick one streamline and you draw a tangent to this stream, so if I draw a tangent on the streamline, let's assume that the direction of velocity is in this direction. You can also find out the direction of velocity by knowing the streamline and just by looking at these velocity components. That's it. So so in the xy plane, see ux is positive and ui is negative, which means my velocities will be in this direction. That is, my velocities will be in this direction. Just just by doing a good, just by having a look, you can also tell what is the direction of velocities. But let's say I know the direction of velocities is in this direction. If you pick a streamline, if you just pick a single streamline and you draw a tangent, okay, this tangent gives us the direct this tangent gives us the direction of the velocity vector v. Okay, a tangent to a streamline give us the direction of the velocity vector. Okay, that is also one of your questions in the assignment. So in a way you got the hint of solving this. And a family of streamline, as I said, it is known as stream tube. So there will be multiple streamlines like this, and this is known as stream tube. Okay. By the way, this kind of form is known as a rectangular hyperbola in mathematics, and this is essentially a rectangular. These are essentially different families of rectangular hyperbolas that we are kind of drawing. All right. I'll I'll also tell one important point here. See, the very definition of defining stream function is that I said that my ux, which is the x direction velocity, is nothing but del psi by del y, and my uy, that is the y direction velocity, is nothing but minus del psi by del x. So always remember the way we define the way we define uh, what we call is the way we define the definition of stream function, the continuity equation is always satisfied. That is something that you should appreciate. For instance, as a proof, I can show that. So can you tell me what is the continuity equation in a simple xy velocity in a simple xy Cartesian plane? Can you tell me? For an let's say for an incompressible fluid, the simplest thing. So I think you guys know at least at this point of time that for an incompressible fluid, the form of the continuity equation in its vector form is that the divergence of the velocity field is zero. Sometimes people also say that the velocity field is solenoidal for an incompressible fluid. It just means that the divergence of this velocity field is zero. So if you write this divergence of this velocity field in Cartesian coordinate, you will just get del ux by del x plus del uy by del y. This is just the divergence. This is just writing a divergence applied over the velocity field in Cartesian coordinate system in the xy plane. That's it. If I have a z component, it would just be del u z by del z. but we are just keeping it simple. We are just writing it the xy plane. Now, if you substitute this form of stream function in the x in this equation, what you will see is it is del x, u of x is just del psi del y, and plus it is del y, u of y is minus del psi del x. Okay, and this can be written as del square psi by del x del y, just simple math, and this is minus del square psi by del y del x can be written as del x del y if psi is a continuous function, and I assume and stream and this and the stream function is a continuous function. Basically it can never be a discontinuous function, because had that been a discontinuous function, you will see a discontinuity in the velocity, which is not possible, because physically a tangent at any point on a streamline should give you the direction of velocity, and had psi been a discontinuous function, your your velocity would be discontinuous, which is not possible because it's a vector field, right? It cannot be discontinuous, at least physically. So this means I can write so I can write del y del. So basically I can flip these things, flip del y and del x, because it's a continuous function. So this just becomes del square psi by del x del y, and this is of course equals to 0, which is your right hand side, meaning that the manner in which you define the stream function, the continuity equation is trivially satisfied. This is something, that I wish to, put forward here. Okay, but here is the thing: is stream function a scalar or a vector? This is something that I want to ask you. It appears though as if like we are dealing with a scalar function, because these are just scalar things that we are doing. But in general, can you tell me, is stream function a scalar or a vector?
It's a scalar.
It's a scalar. It So here is the thing, and here is essentially, the beauty, as I would say. The manner in which we use stream function in our day-to-day, fluid dynamics problem, makes you believe that stream function is a scalar, but essentially it's just a special case in which we treat the stream function as a scalar quantity. And here is something that I'll prove you why this is the case. See, the reason why we can define stream function for incompressible flows is that your velocity is divergence free. I think this is something that you know, and this is nothing but the continuity equation for an incompressible. This is nothing but your continuity equation for an incompressible fluid, meaning that your density is constant. And this is something that you have already saw when you derived the Navier-Stokes equation in your theory classes. Okay, that is divergence of velocity is 0. I'm writing this in vector form for a fluid which is incompressible, meaning that your density is constant. Also, I will not explain it much, but you can also show that if this form of this form of the continuity equation also holds good if the material derivative of density is equal to 0 for the fluid. It holds good if your density is constant, or if this condition is satisfied, that your material derivative of density with time is equal to 0. If any of these two are satisfied, okay, that means your density is not varying with time, it is also not varying with space. Okay, if any of these two conditions are satisfied, you can use basically this form of the continuity equation. I'll not prove this, but if you have doubt, I'll clarify this in the next class, okay? On these two concepts, that why these two cases are sufficient enough to use the divergence free form of the continuity equation. Okay, now the objective is not that. The objective is that if you can define a vector field, a velocity vector field, which has a zero divergence, you can show that if your velocity field has a zero divergence, you can define your velocity as a curl of a function that's a psi bar. Now, this you always need just realize that if this is satisfied, you can write v as a curl of a vector function. Actually, this this vector function that you saw, okay, this vector function that you saw is so there is a question: divergence of v equal to 0, it is incompressible. If it is greater or equal to 0, okay, so I'll come to that. I'll come to that. I'll come to that money, but I'll just finish this and I'll come to your question. Okay. So what I'm trying to say is that if my velocity is divergence free, I can write velocity as a curl of a function, and this is essentially, so this function psi is the more general form of stream function, as I would say. But what we do is, since we tend to use stream function in 2D flows, I generally write this psi bar as psi ez, because I'm writing, because I generally, you know, so it's like it is more convenient to use that form of the stream, that vector form of the stream function in 2D flows, and we will see why basically we'll do that. And for as of today, I'm just giving you an idea that in general stream function stream function is a vector, but the form that we use in 2D flows, it's basically a scalar, and this is precisely the psi that we generally use in stream function, and this is nothing but a scalar quantity which may be a function of xy. It can also be a, so it, in general, it is just a function of xy. Okay. So so whatever size that we wrote here, is basically this. It's actually the magnitude of the stream function vector. So this is known as stream function. This this psi is essentially known as stream function. Okay. And this psi bar is known as stream function vector. Now, it is more customary to use stream function in 2D flows, or at max in axisymmetric flows, and that's why we use this stream function only, which is basically the magnitude of the stream function vector. Its direction, it also, so the stream function vector also has a direction, and its direction in general, it's in the z direction basically, if we are dealing it in the xy Cartesian coordinate system. Okay, I hope this is clear to you. And I also wish to discuss something which is known as the velocity potential. But yeah, before that, and just before finishing, we have time up to 5. So there is a question that divergence equals to 0 it means it is incompressible. So your question is that what is basically this then? Okay. So your question is, what is this then? So if I have a vector field whose divergence is greater than 0, or basically this is something that you are asking. See, in general, there is just these two, I would say, conclusion, that if divergence is equal to 0, it is incompressible. If divergence is not equal to 0, it is basically a compressible fluid. The fluid doesn't care if it is greater than 0. Numerically, you can get a value which is greater than 0. It can be less than 0. But the only criteria, the distinguishable criteria, is that if a velocity field is divergence free, it's a compressible fluid. Okay. Or it's a compressible flow. Okay. Or if it's the other way around, that it is not equal to 0, okay, it is so then we need to look into something which is known as compressible fluid, which is beyond the realm of the discussions of this course. But I can only say that it's basically, so we look into something of a case where the density is essentially changing with space and time. Okay. And this is the hallmark of a compressible flow, where your density is not constant. That's the idea. I mean, that's the answer that I can give, that if your divergence of velocity is greater than 0 or less than 0, okay, it means that the density of the fluid is now not constant, or it can vary with space and with time. Is it clear? I mean, is my answer convincing enough for your question?
Hello, sir. Can you hear me, sir?
Yeah, I can. Yeah, I can.
Yes, sir. So we are calling in that equations. It is incompressible.
Yes.
Um, Somewhere I studied, sir. It is. It means it's a continuity equation. Continuity means it's a fluid. It's a moving, right?
Yeah. Yeah.
A
It's a
fluid.
moving
It's
fluid.
a
Yeah. Yeah.
microscopic way. It's moving.
Yes.
Yes. So if it is less than and greater than, I read something in the textbook. It is a source and sink like that. They said.
Yes. So that is something. So yeah, I understand. See, this. Yeah, I understand what is your problem.
It's
I mean,
greater than zero. It means a source, and less than zero, it's a sink.
yes, I understand what you're trying to say. See, this does not mean that your velocity is greater than 0, or your velocity is less than 0. It just says that if you have a vector field, you calculate the divergence. If it is 0, The fluid is incompressible, but it can still move. It doesn't mean that your
Yes,
velocity
yes,
is zero.
yes. Yes, sir. That's I mean, sir. It's
Yes,
incompressible, and also the fluid
yes,
is a moving.
yes.
If
But
it is static, means it's also equal to zero, right?
yeah, static means velocity is equal to zero. That's the thing. Okay. But let's say I'm considering a moving fluid, and if I find, and if you, so let's say I have a velocity field, and you calculate its divergence, it is not coming out to be equal to zero. The only conclusion, at least the rest assured, the only conclusion I can say that it is not for a, so this velocity field is not for a compressible fluid. That is the safe side definition that I can see. It's so this source or a sink, there is something which is known as potential theory, and potential theories are essentially inviscid. So these are defined for inviscid flows, but this doesn't talk about the compressibility of the fluid. To me, to the best that I know, the source sinks. There's something also which is known as vortex and all those things. These are essentially terms of something which is known as potential flow theory, which is inviscid in nature, meaning that the fluid has zero viscosity, and we will see these things later on. But to me, it doesn't speak about whether it's an incompressible or a compressible fluid is something that I'm not sure about. Okay, but anyways, like if you can have more clarification on where did you read this or which book did you read this, like I can assist you in this regard. But
It's a fluid dynamics rising ania book, sir.
okay,
Yes,
okay,
sir. In that book, sir, yes, sir. If v is a velocity, some it's a vector quantity, sir. It's a
yeah, yeah, I understand.
so
It's
yeah.
yes.
Ah,
So
yes, sir. It's equal to zero. Okay. It is a fluid moving. It's a fluid flow actually.
okay,
It's incompressible. That greater than zero, it is a source. They ask it's a source. Source means it's like a um,
okay.
source.
So yeah, so, okay, sourcing. Okay, okay. All right.
Yes,
So
sir.
what I will do is I'll have a look, because
Okay.
generally what I interpret is like whether it's a fluid. So these are the, so this inviscid, incompressible, and something we'll see which is irrotational, and let's say we'll discuss this in 5 minutes if we have time. I mean if
Yes,
you
sir.
guys
Yes,
have
sir.
time. But these things are, it's they are not exhaustive basically. So like you cannot say that if it's an inviscid fluid, it doesn't mean it necessarily have to be incompressible and so long and so forth. Okay. So what I know is that I just check if I have a velocity field, if it is divergence free, it's a compressible fluid. Or you can say, or you can interpret it as a compressible flow crudely, although there is a little distinction between compressible fluid and a compressible flow. But uh, but like I just treat it as you can say two different subsets basically. In one
Yes, sir.
subset I have,
Actually, sir, one small doubt, sir.
yeah.
That, sir, when it is what I mean is when it equal to zero,
Hmm.
the fluid particles moves in the parallel way.
No, there is one thing that I will clarify. When you talk about these terms like a velocity field is divergence free and things like that, you cannot talk about particles because particles come into the Lagrangian description. Okay? You
Ah,
need to
yes,
talk
yes.
about quantities like field, for instance, velocity field, acceleration field, density field, and things like that. Okay? So
Okay,
that's the first thing.
it's meaning. Okay, okay.
So it
Yes,
may be, so if you speak about Lagrangian description, these are completely different things. So this compressible, incompressible, irrotational, rotational, and inviscid or viscous fluid, these are defined only for a Lagrangian frame of description, and not a, sorry, these are defined only for an Eulerian frame of description and not a Lagrangian frame of description. I hope like you are clear on this. I mean, is it okay?
yes, sir. In that point, I have so many doubts. Okay, okay, sir. Thank you so much, sir.
Yeah, okay, all right. So I'll just end this since you guys have a little doubt on these things. So I'll just end it by defining something by just clarifying something which is known as the velocity potential. Okay, just how we saw that for stream for this this stream function, your flow needs to be incompressible basically. That is, divergence of velocity should be equal to zero. Then you can basically define your stream function. And we saw that in general, stream function is a vector, which we call it as stream function vector. But like it is more customary to use this vector in a scalar form, which is just by dealing with its magnitude in 2D, or at max you can use that in axisymmetric flows. Okay. Now there is one thing, that if your velocity is irrotational, meaning that your curl of velocity is zero, you can show that your velocity can now be written as a gradient of a scalar function. Now remember, this phi is a scalar function now, where this phi is known as velocity potential. Okay. Now, as I said, if your flow is incompressible, you can define stream function. Just now, if that your flow is irrotational, you can define your velocity as a gradient of a scalar function, and the scalar function is known as velocity potential. And you can show that your x direction velocity in Cartesian frame is nothing but del phi by del x, and your y direction velocity is nothing but del phi by del y. Just substitute this here, and you can show that this is indeed satisfied. Just what we did for for stream function. Now the important point is, if your flow is irrotational, meaning you can define a velocity potential, which is a scalar function. Remember, so this phi is a velocity potential and it's a scalar function. Now that it is irrotational and you have defined phi, in addition to this, if your fluid is incompressible, okay, meaning that, so what does it mean? It just means that your divergence of velocity is equal to 0. That is something that we have seen many a times. And your flow is also irrotational, meaning you can write your velocity as a gradient of a scalar function, which means you can write this as divergence of gradient of phi. Because your flow is also irrotational, you can write this velocity as this, and this is basically equal to 0, which means there is a very nice operator which introduces from this that divergence of gradient of any scalar function is equal to del square of phi, and this del square is known as a Laplacian operator. And it is said that if your flow is irrotational and incompressible, your velocity potential function satisfies something which is known as the Laplace equation, and this equation is called the Laplace equation. Okay, this is called the Laplace equation. So your velocity potential satisfies the Laplace equation for a flow which is essentially irrotational, because you are defining phi, plus it also has to be incompressible. Okay, so these are the two basic things that I would like to clarify, and there are many. So I don't know the background of from which streams you guys are here, but if we go into a little bit of deeper mathematics, the solution. So see. If phi satisfies the Laplace equation, the solution of phi is, let's say, phi of some xy, let's say, in 2D space. So these phi of xy are essentially called harmonics. So the function which results as a solution of the Laplace equation are called harmonics, and these functions are known as harmonic function. Now, these harmonic functions have some amazing properties. Okay, for instance, there is something which is known as so the Laplace equation is kind of an averaging. It's kind of an averaging function. Okay, which means that the value of phi that I calculate at the point is essentially its average to the values which are its to its right and to its left, meaning that at least, let's say, I'm just considering for a 1D system, and I'll just end it here. And these are some additional things that I'm saying, that the value of phi is basically the average of phi of x plus a plus phi of x minus a by 2. So phi is basically this, and this is essentially a property of a harmonic function, which are the solution of Laplace equation. So these are some unusual and amazing properties. So if you are from maths background, you can appreciate that although I'm also not from math background, I'm a mechanical engineering student, but these are something that we learn as a part of my research that I do here. But these are some amazing properties of Laplace equation, is that Laplace equation is an averaging function, and it also means that, and a corollary of this definition is that there is no local maxima or minima in Laplace in these harmonics or the solution to Laplace equation. Okay, so these are some important, some properties of Laplace equation that I seek to just tell you, but we will not go into the details of this, because it being a fluid dynamics course and not a maths course. But we will see these kind of equations. We will come across these kind of equations very often. Okay, for instance, there is something which is known as a Stokes law equation, and in Stokes law you will solve something which is known as a biharmonic equation, which is del 4 of the stream function equal to 0. So for instance, if you take a del square of this equation, you will basically get del 4 phi equal to 0. This is known as a biharmonic equation. So all those things, all those terminologies, you will come to the later part of this course. We'll look into something which is known as Cripping flows, where we essentially solve this biharmonic equation to get the answers, to basically come out with the solution and things like that. Okay, But yeah, so these are the things that that I would like to clarify. I mean, we are up with our time, so I'll stop here for today. If you have any questions, you can ask. And I thank you really for actively participating in this session. I hope you will please watch the lecture series, and please and these are just, and what we did here is just the tip of the iceberg. I mean, there are many many fascinating and yet a little bit so as we move on, we'll increase the complexity of things. Okay, these are just some preliminary things that we just learned today, but please keep on and of course it being a postgraduate level course, we we are ought to deal with complexities here in these course. Okay, so please keep watching the lecture series. Please actively participate in the discussion forum, and I thank you for participating here. If you have any questions, you can ask me. I'm here for some minutes. But since we are up with our time, I will not extend the session much more. But I thank you once again for being here, and I hope you will continue participating in the discussion forum. We'll meet again in the next week at the same time using the same link from 3 to 5. Thank you, guys.
Yeah, thank you, sir.
Yeah.
Thank you so much, sir.
Yeah. Thanks. Thanks a lot. Thanks a lot. Okay. If no questions, I'm closing the session. Thank you once again.